Okay, hello physics students. This is Mr. Zafiro. We're going to try doing some video lessons here, see how it goes. We'll learn as we go. We'll all be patient with each other. And I have posted a few things online, or they will be posted online, I should say. Posted this video here that shows you how to use the discussion thread where you can pose questions and I'll try to answer them. That way everyone in the class sees the question. We're going to move on now, and we're going to do some work in section 4.5, all about elastic potential energy. So in the past, you've learned about gravitational potential energy, you've learned about kinetic energy, but there is also the energy that's stored in a spring or an object that is stretched or compressed. You probably experienced this with a slingshot as a kid, or maybe an elastic band. You can use your thumb and finger to shoot it. Now there is a gizmo, and the gizmo is all about finding the spring constant of a particular spring. And here's the situation with this. And what we have here is a little tray, and we're going to put it on the spring. And you see that the spring has been stretched. So the force of gravity is being applied to the spring, and it pulls the spring through a displacement. So if a force is applied through a displacement, then work is being done. And anytime work is being done, you should remember there's a transfer in energy. And we can add more mass to this. And as we add more mass to it, there's a greater force of gravity on it, there's a greater stretch, and the spring is stretched and work is done on it and energy is stored in it. We can add some more mass as well. More stretch, more force from the force of gravity through a displacement causing the spring to stretch. And what I'm doing here is I'm graphing the force versus the stretch, or the force, if you will, versus how much displacement the spring has gone through. I'm going to add some more mass here, and stretches even further. The final mass stretches even further. Now you actually did this lab in grade 11, and when you did this lab in grade 11, you were able to find the spring constant of the lab, and I've done it right here. It's 0.30 newtons per centimeter. And if you remember from a few weeks ago when we were first studying force and work and transfer and energy, I did create for you some force and displacement graphs. And if you remember, if you find the area under here, you can actually find how much work has been done by the force, and therefore how much energy has been transferred into the spring, or how much energy is stored in the spring. Now here's another simulation, and I put the link to it. It's called Hooke's Law simulation from the University of Colorado. It's called Hooke's Law because the gentleman, the professor, the scientist Hooke, was the person who really studied a lot of these springs and how they interacted with forces. And as you see here, I can reduce the amount of force that's being applied. That's the force in the red from this device pulling the spring. I can reduce it, and as you can see, the force from the applied force is always equal but opposite in direction to the spring force. Not because of any great mystery. You've seen things like this. The force from this device on the spring has to be equal in magnitude and opposite in direction to the force of the spring back on the device here. We know Newton's third law. So as one stretches the spring more and more force is needed to stretch it. And as you can see here, as the displacement gets larger, the force needed to pull the spring gets larger, and the force with which the spring pulls back gets larger. What Hooke discovered, the scientist who discovered all this, was that the force required to stretch the spring and the force with which the spring is pulling back was absolutely positively dependent upon the displacement. So the force is not constant. It depends on the displacement here. This is new for us in physics class because most of the forces that we've dealt with have all been constant. Not this. This force actually depends on displacement. Okay, so on to our note here. I've posted a version of this note on my website, and the title is Elastic Potential Energy. So if you can imagine, this is a spring with a mass attached to it right here, and maybe it's sliding along some, let's say it's a frictionless surface, all right? And then let's say I pull the box over and therefore the spring stretches right there. So someone is physically pulling the box and stretching the spring. Well, what we will say is that the spring has a force in the opposite direction here, and it is called the restoring force. Now, if you take a look at this, the restoring force is pointing in the negative x direction because as I've drawn here, this is the positive x direction. And this area here, I've called positive x displacements. So when I pull the object to the positive x area, or the positive end of the number line, the restoring force is actually negative. Now, if I let this go, it would swing all the way back, go through this position right here where x is not positive or negative, but it's 0, x equals 0. And notice it's x with a vector sign there. We call this the rest position, or where there's no stretch and no compression. All right. And then it would fly back into a compression zone. Sorry about that. As I was saying, the object moves past the x equals 0 position and into what we call the compression zone. So now the spring is compressed and it's in the negative x displacement area. All right, x equals 0, positive x displacement on this side, negative x displacement on that side. But if you take a look at this, the restoring force is always in the positive direction now. So when the displacement is negative direction, the restoring force is in the positive direction. When the displacement is in the positive x displacement area, the restoring force is in the negative direction. So that's what we've discovered here in this little drawing here. And this was discovered by a gentleman named Hooke. And that's what I've written out here, that the restoring force follows Hooke's law. The restoring force is linear, and it depends on the displacement from the rest position. So Hooke came up with this formula. The restoring force, F subscript R, is equal to negative K X, where X is the position from the rest position, and K is the spring constant, or the stiffness of the spring, which is measured in newtons per meter. This is something that you did back in grade 11 physics when you actually measured this. And this was also what I was having a look at when I was looking at the spring constant from the gizmo. The slope of this line was the spring constant, and that's what we were calculating there. So back to this. Make sure this goes into your equation sheet. It's a conservative force. All right. It is path independent. It just depends on the position. But what's really important here is the negative sign. Okay? The restoring force is always in the opposite direction of the displacement. If you have positive displacement for the spring and the object at the end of the spring, the restoring force is in the negative direction. If you're in the negative displacement for the object at the end of the spring and the spring itself, then negative times negative and the restoring force will be in a positive direction. And we can see the negative aspect of this, right? That the restoring force is negative kx. We can see that in the diagram that we talked about before. Now, if you wanted to calculate the work done by the restoring force, you could try to use this equation right here. Force restoring dot displacement. And we now know that force restoring is negative kx, and that the displacement, instead of calling it delta D, let's call it delta X. The issue with this is that this force is not constant. We can only use this equation right here if the force is constant. As soon as the force is not constant, what X value do I put in here? Because as I stretched it, the force kept on changing, kept on changing, kept on changing. Where do I pick what X value to put in to represent the force over the entire stretching? You can't. So you literally cannot use this equation to find the work done by this force. This can't be used. Ooh, that's an ugly U. Let me try to fix that. There we go. Purple again. Can't be used. So this next part of the note here is I've actually graphed in red here force restoring versus x position. And force restoring is equal to negative kx, which we can realize if we rewrite this equation as y equals mx plus b, because the y-axis is now force restoring. The x-axis is still x. And if you take a look at this, the y-intercept for this equation, or b, it would have to be 0. And m, which is the slope from the equation from a line, it would have to be negative kx. And if we go back to this, we actually see that, right? As I move this over, I'm changing the slope of the line, and it's actually the k value. So k, the spring constant, is the slope on this force versus stretch graphic. So I've plotted it through here. There you have it. F is equal to negative kx. It has to have a negative slope, and that's why it's sloping down and to the right. So what we're going to do is we're going to make a slight alteration to the graph. Instead of graphing force restoring, the restoring force, I'm only going to graph the magnitude of it. So all of the force restoring's magnitude would be positive, and you would get a line like this. And this represents the force that the spring is applying to the object as it's being stretched. That something else is stretching it, some other external force is stretching it. The spring pulls back with a restoring force. So as X gets bigger and bigger and bigger, as you're pulling the object and stretching the spring further and further and further, the force gets bigger and bigger and bigger and bigger. And you start with 0 stretch, and let's say you end right here, and that's the maximum stretch that you've given it right there. So to get from 0 stretch to maximum stretch, let's say that the spring has gone through a displacement of delta x. Well, I hope you remember from a while ago that I showed you can actually calculate the area under a force versus displacement. displacement graph right there. Okay? And when we calculate that force, excuse me, when we calculate that area under a force displacement graph, that area allows us to calculate the work done by that particular force. So since this is force restoring, we're actually calculating the work done by the restoring force. Now the work done here is going to change the energy of this system. And the energy that's being changed is the energy that is stored in the spring. And we label that as EE, or elastic potential energy. The work that's being done is not an object being lifted into the air. We're not changing the uh, gravitational potential energy. And when I stretch the spring as far as I can possibly stretch it and then stop it, the object's not moving, so there isn't kinetic energy when I've stretched it to its maximum position. So the work that was done had to go somewhere. It went into this new type of energy called elastic potential energy. So the area under this graph is a triangle. So we know that the area of a triangle is half the base times the height. But in this particular case, the base is the displacement, delta x, and we only want the magnitude of it. And the height is the restoring force at maximum displacement. So it would be force restoring at uh, x maximum. And let's call that uh, x right here. Okay, so this spot right here, we're going to label it as x. So from here to here is delta x, and this is maximum displacement x. So what I'm telling you is at maximum displacement, the restoring force is equal to negative kx. And it's in a magnitude sign right here, just like the displacement was in a magnitude sign. Well, if we assume that this started at 0, right? If we assume that this started at 0, then you would have x final minus x initial is your delta x. Well, I just told you that I'm labeling x final as x, and my x initial is 0, so my delta x is also x. So not only do I have an x here, but this delta x becomes x right there. Okay? So now we continue with this. The half continues over. The delta x is x, and the negative kx stays as negative kx. Now these are all in magnitude signs, so I don't really care about the negative signs in there. Look, I got a magnitude sign for that. I've got a magnitude sign for that. So the negatives all go away. And the half comes down. The k, the spring constant, stays, but the x times x gives me x squared, all a very much a scalar equation. So remember, if we go back up to the top here, we're calculating the work done by the restoring force, but we're also calculating the elastic potential energy. So I've come up now with the equation for elastic potential energy. It is equal to half times the spring constant times the displacement squared. So make sure you add this to your equation sheet. This is your second equation already today. So we can then say that work done is equal to the change in elastic potential energy, which is elastic potential energy final minus elastic potential energy initial. I now have an equation for these. Half kx final squared minus half k xi squared. And we have a new member of the family for elastic potential energy. It's a new energy we haven't talked about before. Now, let me do an example here for you. It says calculate the restoring force for a spring with the constant of 3.3 newtons per meter, and the spring has been stretched by 1.5 centimeters. Pretty straightforward. There's your equation right in there. The negative sign comes down. The spring constant comes down, but this is in centimeters. Can't have that. So I convert it to meters, and I know that when this spring has been stretched by 1.5 centimeters, that's the restoring force right there. Now let's say that the spring started at the rest position, and this 1.5 centimeters is as far as it possibly was going to be stretched in this situation. So I can actually calculate the work done to stretch it, and in that case I can calculate the change in the elastic potential energy, which would equal elastic potential energy final, that's a horrible E, there we go, minus elastic potential energy initial, which would equal a half K x final squared minus a half K x initial squared. Now remember what I said. I said let's assume it starts from the rest position where x is 0. So that means that's gone. That whole term is gone. X was 0 at the start. And now I can calculate the work done on the spring, and therefore its newly gained elastic potential energy. It would just be a half K, oops, sorry, K is 3.3 newtons per meter, and x is 0.015 meters, and we have to square it, and square it, there we go, and we could calculate how many joules of elastic potential energy has been gained. So if you go to the website, uh, in the announcement, you'll see I've posted some reading for you to do. I've posted the links to the two animations I've used. I've posted some questions for you to do. I've posted the discussion thread where you can ask questions, and I'm going to do this on a daily basis. That's my plan. And please ask questions. Is it as good as being in the same classroom? No, it's not, but we're going to do the best we can. We're going to be patient with each other, and we're going to all help each other out. Stay safe.